All right, welcome back. It's Mr. A little bit. I mean, like, right now. So, talk more about it now. It's kind of hard to see here, but we can write vectors with bold lettering. All right, what it is. Now, my y component would be 12.99. So, my vector, if I draw this triangle and I say this is x and this is y, all right, I know, excuse me, this should be like that. I know that's the magnitude of my vector, right? So now, let's see, this is trigonometry. This is adjacent over hypotenuse, that's cosine. So I could write the cosine of theta equals my x component over the magnitude. And if I solve that, I would just do the magnitude times the cosine of the theta would equal my x component. Likewise, over here, this is my opposite side, so that's sine. So if I want to find my vertical, I can do sine of theta equals my y component over the magnitude, or simply the magnitude times my y. 15 times sine of 60. All right, over here. Here I had 6 times cosine of 160. I got negative 5.64. That should make sense. 160 is over here in the second quadrant, right? So that means my x value is a negative because it's going to the left. My sine should be positive because I'm still going up. That'd be 6 times sine of 160, excuse me. And that's 2.0 5. When I multiply by a negative scalar, 2, 1, 2, 3, then 3, 4, 5. That's my first vector. And then 3, 1, 2, 3, down 2, 1, 2. That's my second vector. You'll see it doesn't matter which way I go. Tip to tail, they add the same. And we are going to use this, all right? Next lesson, we're going to use this. We drew a parallelogram, and there's some really great things about parallelograms. That are going to help us out. Then find the components down here. All right, go ahead and try that, comma, negative 6.43. Vectors part 2. And hey, helps us magnificently, I love that word, to find the angle between the two vectors. So let's take a look. So it says find the angle between the two vectors. So now I know a couple of things. I know one way to find it would be to do a1 times a2 plus b1 times b2. And I know that is the same as finding the, I'm going to call this u and this v. All right. The magnitude of u times the magnitude of v times cosine of the theta, the angle between them. All right, so let's see what I can do here. I have negative 3 times 2 plus 4 times 6. So this is negative 6 plus 24, which is 18. All right, great job. All right, over here on the side, let's find some magnitudes. So let's find the magnitude of u. The magnitude of u is negative 3 squared, 9, plus 4 squared, 16, right? And that gives us 9 plus 16, 25. Ooh, look at that. That's nice and neat. 5. Let's find the magnitude of v. The magnitude of v is 2 squared, 4, plus 6 squared, 36, which is 40. And I'm going to leave it as 40. I'm not going to simplify it or anything like that. I'm just going to put these in here. So 5 times square root of 40 times the cosine of theta. All right, so I'm going to bring this down now. I have 5 radical 40 times the cosine of theta. I'm going to divide both sides by 5 radical 40. At this point, this is calculator work. So I'm going to divide 18 divided by 5 radical 40. Make sure this whole thing is in the denominator. All right? So what I get there is 0.569. All right? Now, for those of you at home, this is definitely not all of what I'm doing, right? There's many, many more decimal places. So the next part of this, when I do this, I need you to understand I'm not putting in 0.569. I'm putting in everything in my calculator. Everything in my calculator was 0.56920997888, and it goes forever. That's what I'm putting in. So if you put in just 0.569, you're going to round too soon. Don't round too soon. So I need to find the inverse of that, right? And that'll give me my angle. And when I did that, I found that my angle was 55.3 degrees. All right. So again, let's think about this. What does this represent? So -3, 1, 2, 3, up 4, 1, 2, 3, 4, like this vector. This is just an approximation. And this vector, 1, 2, and up 6. Again, I didn't draw it perfectly. They're saying the angle between them, right here, that equals 55.3 degrees. That's actually pretty close, doesn't it? All right. So you try this one. Maybe sketch it out at the end to see, or maybe sketch it out at the beginning to see what you think it might be. But you go ahead and try this one on your own. So over here, I found the magnitudes. I got the magnitude of A was radical 34, and the magnitude of B was radical 136. I plugged in my formulas on this. I noticed that on the left side, the easy side, I got 30 plus negative 30 or 0. Over here, when I multiplied my magnitudes together, remember when they're both under a square root, you can multiply them together. So I got 4,624, square root of that. Divide, I got 0 equals cosine of theta. Well, I know 300 and now I'm telling you, sorry, we're not going to go that in depth. We're going to use them for vectors. If you want to study more about the law, there's the ninth plane. This, but I r here, which is c squared equals a squared, and someone is equal all that's per hour. So now the plane is inclined. What here with the horizon? This is here, but I can't do that until I find that whole big angle. I haven't. So it's one in here. 7. I need right here. This whole angle was 57, and I knew that was 40 plus some other part going. Welcome back, Sully here. We're going to be talking about something that is something we kind of referenced earlier, parametric equations, and also vectors. And it's called vector valued functions. Vector valued functions, right? And a lot of this has to deal with how we talk about the motion of particles. So I have this wonderful picture of things that might be particles moving around, dancing, all right? So here we go. Let's take a look. So the position of a particle moving in a plane that is given by a parametric function, x of t, y of t, so two functions making up like a vector, may be expressed as a vector valued function. So we can take this and express it as a vector valued function. In other words, we can plug in our t, find our x component, plug in our y, find a y component, all right? Or we can have these being functions right here. The magnitude of the position vector at the time t gives us the distance of the particle from the origin. So let's take a look at one. Consider the vector valued function. So we have our x component function is t plus 2, and our y component function is t squared. So for t is negative 2, I would plug in negative 2. I'd get 0 for my x, and I would get 4 for my y value. Now, it's very common to think of this as a coordinate, but it's not. It is a vector, so I'm going 0 and up 4. All right, I want you to remember that. Now, the location is the endpoint. That's where the particle is. If I took the magnitude of this, which one, this would be very easy. 0 squared plus 4 squared is 16. The square root of 16 would be 4. So that would be the distance the particle is from the origin. All right. All right, let's do the next one. Plug in negative 1. Negative 1 plus 2 is 1. Negative 1 squared is 1. Over 1 up 1. Again, that is now the position of the particle with that vector. Plug in 0. 0 plus 2 is 2. 0 squared. Now we have a third position of our particle. And we have a graph kind of forming here. All right. Plug in 1. 1 plus 2 is 3. And again, here's the tricky part. I've done this myself before. Don't tell anybody. Once you get this part, you're like, oh, I'm going to plug that in. But I'm always plugging in my value of t, right? So 1 squared is 1. So 3 over, 1 up. This is our fourth vector location, right? And 2. 2 plus 2 is 4. 2 squared is 4. 4 over, 4 up. That's our last vector location. All right, now, here's the thing. What kind of shape is being formed? Now, I'm going to take away the vectors and just have the endpoints. All right, and you'll see in the answers that I really just have the endpoints because that's what we're talking about. We're talking about where the position is they're at when at time negative 2, right? Or time 0. So, what does that form? Oh, this one forms a quadratic. Now, you're going to see some pretty interesting formations as you go through these, depending on things. For example, you could have your x value be t squared and your y value be t plus 2. And that would change things up, all right? Your graph might be something that doesn't look like a normal function, all right? So keep that in mind as you go along. But here, the key here is I really want you to remember, these are vectors. They're not coordinates. It's the endpoint of that vector that gets you here. All right? Subtle difference, very subtle difference. I totally understand that, but that's what I need you to think about as you're going through this. All right, when we looked at these vector valued functions, we need to talk about a couple of things. Number one, the domain of a vector valued function is the intersection of the domains of both of the component functions. So the domain of the x component and the domain of the y component, that's going to be the domain of our vectored valued function. So if we take a look here, let's find the domains of each of the components and then of the vector valued functions in total, all right? Let's recall a few things. Domain. We have a couple of rules, right? Number one, we cannot divide by 0. That's a big one. Number two, we cannot take the square root or actually any even root of a negative number. Okay, those are like the biggest quantifiers for domain. So let's take a look here. T squared minus 3. All right, so am I dividing by 0? Or am I dividing by anything that could possibly equal 0? No. Am I taking the square root of anything or an even root of anything? No. Are there any disqualifiers here? Can I put any value of x in? Yeah, I can. So for my x component here, my x component would be all real numbers. Remember, we write it like that, or you could say all real numbers. Over here, we definitely have a problem here. We cannot divide by 0. So when does t minus 2? It cannot be 0, so t cannot equal 2. So our y component is going to be from negative infinity to 2 and from 2 to positive infinity. Because it's all the real number, it can be any number other than 2. All right. So then our vectored value function would be the domain of that. It's where these two overlap now. This says it can be any number, and this says it can be any number but 2. So the intersection here is actually just going to be this y component. All right. So let's try one that maybe has a little bit more qualifiers. Let's look at this one. This function, we have a square root issue. And I know that inside here, x plus 4 has to be greater than or equal to 0, right? Because it cannot be a negative number. So x has to be greater than or equal to negative 4. All right, so my x component is going to be negative 4, all right? And it could equal that, couldn't it? All right, and it's going to go, all these are good functions, so the one moving left. Positive 5 times the cosine of pi over 3 is 1. The one component is positive. 2 radical 3 squared. 1 squared is 1. 2 radical 3 squared is 4 times 3, 12. So our speed is radical 13, or I'm going to put approximately 3.6. All right. That way we have a speed, so it's moving right and up at a speed. X component is positive and up because the y component is positive. Now I can also find the speed it's traveling at. We're going to find the magnitude of that vector. So 1 squared plus 2 radical 3 squared. 1 squared is 1. 2 radical 3 squared is 4 times 3, 12. So our speed is radical 13, or I'm going to put approximately 3.6. All right. That way we have a speed, so it's moving right and up at a speed of 3.6. Now, in this case, we'll call it units. We don't have any units in particular that we're talking about right here, but if it gave us units, we could use units to find that, all right?